Hey there. Ready to dive into some seriously mind-bending physics?
Oh, yeah.
Today, we're tackling a theory that could completely change how we think about gravity.
Okay.
That force that keeps your feet on the ground and the planets orbiting the sun.
It's a concept so fundamental
Yeah,
that we rarely stop to question it.
right.
But that's exactly what we're doing today, exploring the idea that gravity might not be a pull from mass,
Oh, well,
but a push from the vacuum of space itself.
I know, right? It sounds wild. But stick with us. We're going deep into Chapter 5 of Larkey's documentary script, Gravity as a Push, Replacing Dark Matter and Dark Energy, which is part of their trilogy, Gravity and Creation.
You see, traditionally, we explain the universe's mysteries with things like dark matter, to explain why galaxies spin faster than they should, and dark energy to account for the universe's accelerating expansion. But what if we've got it all wrong?
That's where Larkey comes in, throwing out the rule book and saying, hold on, what if it's the vacuum of space itself pushing outward? It's like turning the whole concept of gravity inside out.
Yes.
So how does this even work? Is there like some kind of cosmic plunger out
Well,
there?
not exactly a plunger, but Larkey proposes that the vacuum of space isn't just empty. It's filled with subtle magnetic fields, which they call SMF, and something called the relative vacuum of space, or RVS. These elements interact to create an outward pressure. Instead of mass attracting mass, it's the vacuum pushing everything together.
Okay, I'm trying to wrap my head around this. So instead of the Earth pulling an apple towards it, the apple's being pushed towards the Earth by the vacuum of space. It's like the apple's being squeezed in from all sides.
That's a great analogy. It's
Yeah,
like everything in the universe is embedded in this invisible pushing fluid. And the amazing thing is that even with this radical shift,
right.
Larky's equation for this gravitational push still results in the same inverse square law we observe with gravity. The closer objects are, the stronger the push they feel, just like we see in the real world.
So the math checks out, which is a good sign.
Yeah.
But how does this push theory actually explain some of those big cosmic puzzles? Like, for example, how galaxies rotate.
Ah, yes, the flat rotation curve problem.
Right.
Imagine a galaxy like a spinning disk.
Okay.
Based on the visible matter we see, stars at the edge should orbit much slower than stars closer to the center, just like planets in our solar system.
Right, because there's less mass pulling them inward as you get further from the center.
Exactly. But that's not what we observe. Stars on the outskirts of galaxies are zipping around much faster than they should be, based on the visible matter alone. The traditional explanation for this is that there's a halo of dark matter surrounding each galaxy, providing the extra gravity to hold those speedy stars in orbit.
So dark matter acts like this invisible scaffolding, keeping the galaxy from flying apart.
Exactly.
But with Larky's theory, we can ditch the dark matter scaffold altogether.
Precise. If gravity is a push from the vacuum, that push would be relatively consistent across the entire galaxy. Stars on the edge would experience the same outward pressure as stars near the center, neatly explaining their high speeds without needing to invoke dark matter.
Wow, that's pretty elegant. It's like dark matter was a placeholder, and this push theory fills the gap in a much more fundamental way.
Exactly. But the push theory doesn't stop there. It can also explain things like gravitational lensing, which is how light bends around massive objects like galaxies.
I remember hearing about that. It's how astronomers can see things that are hidden behind other objects, right?
Yeah.
Kind of like a cosmic magnifying glass.
You got it. And one of the most famous examples is the Bullet Cluster, where two galaxy clusters have collided. Now, in this collision, the hot gas from each cluster interacted and slowed down. However, the gravitational lensing effect, the bending of light, was offset from where most of the visible matter was located.
So the light wasn't bending where it should have been based on the visible matter alone. That's where dark matter comes in again, right? The idea is that dark matter, being collisionless, passed right through the colliding clusters, leaving its gravitational signature behind.
Exactly. But with the push theory, you don't need dark matter to explain this offset. Larkey proposes that it's the vacuum field itself that's collisionless, meaning it can pass through the colliding clusters without being significantly affected.
Okay, so instead of dark matter, it's the vacuum field that's doing the lensing. And this field gets all warped and distorted by the collision, which explains why the light is bending in unexpected ways.
That's a great way to put it. And this is what makes the push theory so compelling. Instead of needing these separate, mysterious components like dark matter and dark energy to explain different phenomena, we have this single framework, this outward push from the vacuum that can potentially account for it all.
That's incredibly mind-blowing. a single unified explanation for all these cosmic mysteries. But I'm guessing there's still a lot of scientists who are skeptical. I mean, this is a pretty radical departure from everything we thought we knew about gravity.
Oh, absolutely. This is a paradigm-shifting idea, and it's going to take a lot of evidence to convince the scientific community. But that's the beauty of science. It's a process of constantly questioning, testing, and refining our understanding of the universe.
Well said. So we've talked about galaxies and lensing, but what about the biggest picture of all? The universe is expanding, and not just expanding, but accelerating. How does this push theory fit into that?
That's where things get really interesting, and we'll dive into that right now.
All right, so we were about to tackle the big question. How does this push theory explain the expansion of the universe? It's not just expanding, it's speeding up, right?
That's right. The discovery of the universe's accelerating expansion was a huge shock. Gravity, as we understand it, should be pulling everything together, putting the brakes on the expansion. But something seems to be pushing everything apart, which is why scientists came up with the idea of dark energy.
Right, dark energy is like this mysterious force that's counteracting gravity on a cosmic scale. So how does the push theory offer a different perspective?
Well, if the vacuum of space is already pushing outward, that same push could be what's driving the acceleration.
Okay.
Larkey's theory suggests that this outward pressure from the vacuum itself is enough to overcome gravity's pull and make the universe expand at an ever-increasing rate.
So instead of needing this mysterious dark energy, it's just the vacuum doing its thing, pushing, pushing, pushing. It's like the universe is a giant balloon being inflated from the inside out.
That's a good analogy. And Larkey has even shown how the mathematical model of a push-based universe can actually replicate the observed data from supernovae that originally led scientists to the concept of dark energy.
So it's not just a cool idea. The math actually backs it up. That's impressive. But I'm starting to wonder, if this vacuum push is happening everywhere all the time, wouldn't it affect things on much smaller scales too, like at the level of atoms and particles?
That's a brilliant question, and you're right on the money. Larkey's theory doesn't just stop at the scale of galaxies and clusters, it delves all the way down to the quantum realm.
Now, for those of us who aren't quantum physicists, what does that actually mean? We're talking about the world of atoms and the particles that make them up, right? How can the vacuum of space influence something so tiny?
Think of it this way. Remember those subtle magnetic fields and the relative vacuum of space, the SMF and RVS that create the push?
Yeah, they're like the unsung heroes of this whole theory.
Well, Larkey suggests that these fluctuations in the vacuum, these SMFs and RVS, could be influencing the behavior of particles at the quantum level.
So are we saying that the vacuum is like a puppet master, pulling the strings of all those tiny particles?
It's more like the vacuum is the stage and the particles are the dancers. It's not controlling them directly, but it's shaping the space they move in, influencing their interactions.
That's pretty wild. But quantum mechanics is already mind-boggling on its own. How does this push idea fit into the whole picture?
Well, one of the biggest mysteries in quantum mechanics is something called quantum entanglement. This is where two particles can be linked together in such a way that they instantly influence each other, even if they're light years apart.
I've heard about that. It's like they have this spooky telepathic connection.
Exactly. And traditional quantum mechanics doesn't really explain how this entanglement works. But Larkey suggests that the vacuum, this interconnected web of energy, could be what's facilitating those instantaneous connections.
So instead of these particles sending secret messages faster than the speed of light, which is supposed to be impossible,
They're actually connected through the vacuum, which acts like a kind of cosmic internet, allowing for instant communication.
whoa. So the vacuum isn't just pushing things around. It's like a giant communication network connecting everything in the universe.
That's the idea. And this could be the key to finally unifying gravity, cosmology, and quantum mechanics under a single framework.
A grand unification theory, the holy grail of physics. It's like finding the missing piece that connects all the different sections of a giant puzzle. But, let's be real, this push theory is still very much on the fringe. There's a lot of skepticism in the scientific community, right?
Of course. And that's healthy. Extraordinary claims require extraordinary evidence. But the potential payoff of this theory is enormous. If it turns out to be true, it would revolutionize our entire understanding of the universe, from the tiniest particles to the grandest cosmic structures.
It's definitely making me rethink everything I thought I knew about the universe. It's like suddenly seeing the world in a completely different light. And speaking of light, I can't help but wonder, how would this push theory affect our understanding of the Big Bang, that moment of creation when the universe burst into existence?
Now you're asking the really big questions, and that's exactly what we're going to explore in the final part of our deep dive.
Let's get to it. Okay, so we've journeyed from galaxies to quantum particles, all under this radical new idea of gravity as a push. Now let's rewind all the way back to the very beginning, the Big Bang. It's the ultimate origin story, right? The universe exploding into existence from a single point. But how does this push theory change that picture?
The traditional Big Bang model starts with a singularity, this infinitely dense hot point containing all the matter and energy of the universe.
Right.
Then, bam, it rapidly expands outward, creating space and time as we know it. But there's still a lot of questions about what triggered that initial expansion, a period called inflation.
Right. Inflation is this super fast expansion that supposedly happened in the first fraction of a second after the Big Bang. But it's still a bit of a mystery.
Yeah.
Like, what powered this sudden growth spurt of the universe?
That's where Larkey's push theory offers a fascinating alternative. Instead of everything starting from a single point, imagine the vacuum of space itself undergoing a kind of phase transition. Think of it like water freezing into ice. It's still H2O, but its structure and properties change dramatically.
So are you saying the vacuum of space froze in a way?
In a sense, yes. Imagine the vacuum transitioning from a high-energy chaotic state to a lower-energy, more ordered state.
Okay.
And this transition would have released a tremendous amount of energy.
Which could be the energy that fueled the Big Bang. And instead of a separate inflationary period, the outward push from the vacuum itself could be what drove the initial expansion.
Exactly. It's like the universe didn't explode from something. It emerged within the vacuum as this phase transition unfolded. The Big Bang wasn't a bang at all, but more like a cosmic sigh of relief as the vacuum settled into a new state.
That's a beautiful image, the universe exhaling into existence. It's so much more elegant than this idea of a singularity exploding out of nowhere.
And it highlights the central role of the vacuum in this theory.
Right.
It's not just an empty backdrop, it's an active participant in the universe's evolution, shaping everything from the largest scales to the smallest.
So this push theory is pretty mind-blowing, but I'm also wondering if it's so revolutionary, why haven't I heard of it before? Is it just too out there, too radical for most scientists to take seriously?
It's definitely a paradigm shift, and like any new scientific idea, it needs to be rigorously tested and scrutinized. There are a lot of brilliant minds working on these questions, and it will take time and further research to see how well Larkey's theory holds up against existing evidence and future observations.
Right. It's not like one theory instantly overthrows everything we thought we knew.
Yeah.
Science is a process. It's about asking tough questions, testing ideas, and sometimes letting go of old models when better ones come along.
Exactly. And that's what makes science so exciting. It's a journey of exploration and discovery.
Yeah.
And even if Larkey's theory doesn't end up being the definitive answer, it's pushing the boundaries of our understanding and forcing us to consider new possibilities.
Well said. It's like we've been staring at a puzzle for centuries, and Larkey has come along and suggested a whole new way to fit the pieces together. Even if it turns out some pieces don't quite fit, it's still opened up a whole new perspective.
And that's the beauty of exploring these kinds of ideas.
Right.
They challenge our assumptions, inspire new questions, and ultimately lead us closer to a deeper understanding of the universe and our place within it.
So as we wrap up our deep dive into the mind-bending world of L.S. Larkey's Gravity as a Push, what's the one thing you want our listeners to take away from this conversation?
I think the most important takeaway is the power of questioning. Don't be afraid to challenge conventional wisdom, to explore unconventional ideas, and to keep asking, what if? The universe is full of mysteries, and the answers may lie in places we never expected.
Beautifully put. So to our listeners out there, keep exploring, keep questioning, and keep those minds open to new possibilities. Because who knows, maybe one day you'll be the one to unlock the next great scientific breakthrough. Thanks for joining us on the Deep Dive.